Hello. Hello, hello. Good afternoon. I'm Bryna Krah. I'm president of the AMS, and it's my pleasure to welcome you to the Colloquium Lectures. These are the oldest lectures at the meetings of the AMS. The first meeting was held in 1895, the second in 1896, where the first Colloquium Lectures actually took place. And those were at Northwestern University, and since that's my home institution, I can't help but mention that. The list of speakers is a veritable who's who in mathematics, including Birkhoff, Morse, von Neumann, Tarski, Chern, Milner, Smale, Nirenberg, Tate, and the list of people I've left off is, well, equally prestigious to those that I included. And amongst them was also our speaker's today's advisor, Ilya Stein. So with that, I'll turn to the introduction of Terry Tao. Terry may be somebody who doesn't need introduction. After all, he's been in a crossword puzzle as a clue in the New York Times crossword puzzle. I don't want to use up all his time by listing the awards he's won, but I could. I'll give you just a short list of the highlights of the Fields Medal in 2006, a MacArthur Fellowship. He's a fellow of the Royal Society, the Australian Academy of Sciences, the American Academy of Arts and Science, and a member of the National Academy of Science. And of course, he's a fellow of the AMS, most important of those distinctions. He has over 350 publications, meaning he hasn't slept in a few years. And this includes numerous highly influential texts. And he has more than 50 collaborators, and maybe that's when I counted last week, so I don't know, maybe this week there's more. He's also one of the broadest researchers in mathematics, covering interests from pure to applied, and I won't list all of the subjects. But it's not only research, he also serves the profession in numerous ways, and starting in 2021, took on a very substantial role. He was appointed by President Biden as a member of the President's Council of Advisors on Science and Technology. So he's a force. He's mentored over 20 PhD students, and I could go on and on. So I've known Terry for a while, since about 2004 or 5 when we first met. But one of my fondest memories of him was at a party that I was a co-host for in 2008. It was the election night, and Terry was sitting in the corner, November 2008, on his computer, on some website that was giving election returns, announcing the states before the TV was. It was really impressive, and it's just one of my fondest memories. Anyway, I won't keep you any longer. It's my pleasure to introduce Terry.
All right, thank you very much, Bryna. I'm very happy to be here at this JMM to give this lecture. It's always nice to be up in San Francisco. So I'll be talking about what I think is a really exciting development in mathematics. It's going to shape our future, which is really the development over the last few years of lots of technologies to make machines and computers help us do math much more effectively. Now this, to some extent, this is not new. We have used both machines and computers, and I use the terms slightly differently. We've used both actually for centuries, really. Nowadays, computers and machines, when we talk machine-assisted mathematics and computer-assisted mathematics, they're sort of synonymous. Initially, they weren't, because computers used to be human, and then they were mechanical, and then finally electronic. So, for example, maybe one of the earliest use of computers was to build tables. So, for example, the log tables of Napier and so forth were basically built by lots and lots of human computers. And those are the earliest examples of somehow computer-assisted mathematics. And tables are still really important today. I mean, not so much the log tables anymore, but a lot of what we call experimental mathematics is based on creating lots and lots of large tables of interesting things, especially in number theory. So, for example, famously, the Legendre and Gauss built tables of prime numbers, and they use that to conjecture the prime number theorem, which is, of course, now a theorem. And similarly, in the 60s, Birch and Swinton Dyer created lots and lots of big tables of elliptic-curves and their ranks and so forth, and this was a key input in formalizing the famous BSD conjecture. And maybe the biggest table of all in mathematics is the OEIS, Online Encyclopedia of Mathematical Sequences. So it's a database of hundreds of thousands of integer sequences, and every day I think mathematicians discover unexpected connections, or maybe rediscover an existing connection. You know, I myself use the OEIS. You know, if there's a quantity which I know there's a formula for, but I can't remember it, you know, if I can just compute the first 5 elements, put in the OEIS, I can usually find it. And most recently, people are starting to use large databases of mathematical objects as training data for neural networks. And so I'll give you one example of that later. So that's one very storied and antique way of using computers in mathematics. The other big use, of course, is in numerics or scientific computing. And that's also a very old subject. Arguably the first big scientific computation was in the 20s when Terence was asked to model the fluid flow for the construction of a new dike in the Netherlands. And so he assembled a team of human computers, basically, to model what would happen to the water flow and so forth. It's notable for the introduction. He's almost the first place where floating point arithmetic was introduced. And of course, we use scientific computing nowadays to model PDEs, to solve large systems of equations. And of course, we use them for computer algebra packages, you know, Magma, Maple, Sage, and so forth. Yeah, you want to do a big, you know, numerical integration or algebraic, you know, computer Grosvenor basis or whatever. You know, we routinely do this now, all across mathematics. Of course, the numerics are sometimes inaccurate. You know, there are round-off errors and other possible problems, but there are ways to make the computation more rigorous. For example, instead of floating point arithmetic, if you use interval arithmetic, if you represent numbers by error ranges, a lower and upper bound, and you keep those bounds like rational numbers, like finite precision, like infinite precision, then you can avoid errors, at least in principle, at the cost maybe of making the runtime longer. More recently, there are more advanced algebra packages than just sort of the standard things you get in Sage or Mathematica. There are these things called SAT solvers, satisfiability solvers, or satisfiably modular theory solvers, SMT solvers. So a SAT solver gives you feed it a whole statement, a bunch of propositions, P1, P2, P3, and so forth, and you say that P1 and P2, or P3 is true, but P3 and P4 and not P5, one of them is true, and so forth, and it will try to see if there's a solution or not. And many problems can be phrased as a SAT problem. So if you have a general purpose SAT solver, you can potentially just feed it into such a program and solve the problem for you. Then there are these more sophisticated variants, SMT solvers, where you also feed laws of algebra, or so you have some variables, and you assume that there's certain laws of these variables obey certain laws, and you ask, can you deduce a new law from the laws you already have? So those are potentially very powerful. And unfortunately, SAT solvability is an NP-complete problem. Once you get hundreds and hundreds of these propositions, it becomes very hard to actually solve these problems. But still, they are very useful. Here's a typical application of a SAT solver. So a few years ago, there was this famous problem in combinatorics called the Boolean Pythagorean triples problem. And so the problem is this: you take the natural numbers and you color them into two color classes, red and blue. And you ask, is it always the case that one of these color classes contains a Pythagorean triple, three numbers a, b, and c, such that a squared plus b squared equals c squared? And it turns out to be, we don't have like a human proof of this statement. But we know it's true now because of a SAT solver. So there was a massive computation that says that if you only go up to 7,824, then you can't do this. There is a way to partition the numbers from 1 to 7824 into two classes, neither of which contain a Pythagorean triple. But once you go up to 7825, no matter how you do it, you must always get one of the two color classes must have a Pythagorean triple. In principle, this is a finite computation because there's only 2 to the 725 different ways to compute different partitions, and so you can just check each one, but that is computationally unfeasible. But with a SAT solver, you can rephrase this problem as a 3 satisfiability problem. It's not just a matter of running the solver, you have to optimize it and so forth, but it is possible to actually solve this problem. And it gives you a certificate, it gives you a proof. And actually, this is, at the time, it was actually the world's longest proof. The proof certificate, first of all, it took 4 CPU years to generate, and it's a 200 terabyte proof, although it is compressible. I think it is still the second largest proof ever generated. Okay, so that's, but this I still consider sort of a more classical way of using computers. But what I think is exciting is that there are a lot of new ways that we can use computers to do mathematics. Of course, there's sort of the boring ways. We use computers to do emails and write LaTeX and so forth. I guess I don't mean that. But there are sort of 3 new modalities, which individually they still have somewhat niche applications. But what I find really interesting is that they can potentially be combined together. And the combination of them, it could be something general purpose that actually a lot of us could use. So the 3 sort of new things. So the first is sort of machine learning algorithms, where you have a problem, and if you have a lot of data for that problem, you can set some sort of specialized neural network to train it on that data, and it can generate counterexamples for you, try to generate connections. And so people are beginning to use this in all kinds of fields of mathematics. I'll give you some examples later. So that's one development. Maybe the most high-profile development is large language models like ChatGPT. These are very general purpose models that can understand natural language. To date, they have not been directly used for so much mathematics. I'm sure many of you have tried talking to GPT, asking it to solve your favorite math problem, and it will give you some sort of plausible-looking nonsense in general. But when used correctly, I think they do offer a lot of potential. I mean, I have found occasionally that these models can be useful for suggesting proof techniques that I wasn't initially thinking of, or to suggest related topics or literature. They're actually most useful for sort of secondary tasks. Okay, so for actually doing math research, they still haven't really proved themselves. But for doing things like writing code or organizing a bibliography, like a lot of the other more routine tasks that we do, actually these LLMs are very useful. But the third new technology, which has been around for 2 decades, but has only now sort of becoming ready for prime time, are these formal proof assistants, which are languages designed to verify, many of them actually were designed to verify electronics, but they can also verify mathematical proofs. And crucially, they can also verify the output of large language models, which they can fix the biggest defect in principle of the LLMs. And they allow new types of ways to do mathematics. In particular, they can allow really large-scale collaborations, which we really can't do without these formal proof assistants. And they can also generate data, which can be used for the other two technologies. So I will talk about each of these 3 things separately, there's beginning to be experiments to combine them together. But they're still kind of prototypes right now. But I think the paradigm of using all of them and also combining with the computer algebra systems and the SAT solvers into one integrated package, it could really be quite a powerful mathematical assistant. Okay, so let's talk. I think my first slides begin with proof assistants. Computer-assisted proofs are not new. Famously, the four-color theorem in 1976 was proven partly by computer. Although at the time it was, by modern standards, we would not call it a fully formalized proof, the 1976 proof. the proof was this long document with lots and lots of subclaims, which like a lot of them were verified by hand, and a lot of them were verified by both electronic computers and human computers. And I think one of the author's daughter actually had to go through 500 graphs and check that they all had this discharging property. And actually, it had a lot of mistakes too. So there was a lot of minor errors in the proof. They're all correctable, but it really will not meet the standards today of a computer verified proof. The first proof, okay, so it took 30 to 20 years for an alternate proof, the four-color theorem, to be verified. And this proof is closer to being completely formal. So it's about 10, 15 pages of human-readable argument, and then it reduces to this very specific computation, which you can run. Anyone can just run a computer program in whatever language they like to verify it. So it was a computer verifiable proof. But it still wasn't a formal proof, it wasn't written in a formal proof language, which was designed to only output correct proofs. And that had to wait until the early 2000s, when Werner and Gontier actually formalized the entire four-color theorem in one of the early proof-assistant languages, Coq in this case. So, I mean, now we know with 100% certainty that the four-color theorem is correct. Well, modulo, trusting the compiler of Coq. Okay, but all right. Another famous machine-assisted proof, well, actually initially human proof, but eventually computer verified, was the proof of the couplet conjecture. So the couplet conjecture is a statement about how efficiently you can pack unit spheres in the plane. And so there's a natural way to stack unit spheres, and it's the way that you see oranges stacked in the grocery store. It's called the hexagonal close packing. And there's also a dual packing with the same density called the cubic close packing. And they have a certain density, pi over 3√2. And this was conjectured to be the densest packing. So this is an annoyingly hard statement to prove. It's an optimization problem in infinitely many variables. So there's each sphere has a different location, and there's an infinite number of spheres. So you're trying to prove an inequality involving an infinite number of variables involving solving an infinite number of constraints. So it doesn't immediately lend itself to computer verification. But even in the 50s, it was realized that possibly this could be done by some sort of brute force computation. And so Toth proposed the following paradigm. So every time you're sphere packing, it comes with what's called a Voronoi decomposition. So every sphere comes with a Voronoi cell, which is this polytope of all the points that are closer to the center of that sphere than to all the other spheres. And this partitions space into all these little polyhedra, these Voronoi cells. And there are various relationships between the volumes of these different cells. There's only so many spheres that you can pack next to one reference sphere, and this creates all these kind of constraints. And so the hope was that if you could gather enough inequalities between adjacent Voronoi cells, the volumes of adjacent Voronoi cells, maybe every such system of inequalities in principle gives you an upper bound on the density of a sphere packing. And in principle, if you get enough of these inequalities, maybe you could actually get the optimal bound of 3√2. So people tried this approach for many, many years, and including some false attempts. But they were not able to actually make this approach work. But Thomas Hales, and then later with a collaborator, was able to adapt this approach to make it work in a series of papers from 94, 98. But he had to modify the strategy quite a lot. So instead of using the Voronoi decomposition, there was a more complicated decomposition that was used. And instead of using volume, they had to define this new score function attached to each polyhedron. But basically, the strategy was the same. And he was able to prove lots and lots of linear inequalities between the scores of adjacent polyhedra. And then just using linear programming was able to then get a bound. And with the right choice of score and the right choice of partition, it was the optimal bound. It's a very flexible method because you have lots of ways you can do the partition and lots of ways that you can do the score. But it was actually, the problem is that it was too flexible. So here's a quote from Hales. says that Samuel Ferguson, who was Hell's collaborator, and I realized every time we encountered difficulty solving the minimization problem, we could adjust the scoring function to score the difficulty. The function became more complicated, but with each change, we could cut months or years from our work. This incessant fiddling was unpopular with my colleagues. Every time I presented my work in progress at a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with what it did in earlier papers, and this required going back and patching the earlier papers. So the proof was a mess, basically. They did eventually finish it in '98, and they were able to derive the Kepler conjecture from a linear programming computation, from a very complicated optimization program. Initially, it was done by hand, but with the increased complexity, there was no choice but to make it more and more computer-assisted. So when the proof was announced, the proof had, it was a combination of 250 pages of notes and lots and lots of gigabytes of programs and data. And it was famously hard to referee. It took 4 years for annals to referee the paper with a panel of 12 referees. And even then, the panel were only 99% certain of the correctness of the proof, and they couldn't certify the corrections, the calculations. Because, I mean, in principle, like, it was all doable, but, like, you know, the referees have to sort of implement all these different computer calculations themselves. But it was eventually accepted. But clearly, there was this big asterisk. There was a lot of controversy about whether this was really a valid proof. And so this was one of the first really high-profile uses of formal proof assistance, because this was a result in which there was serious doubt about the correctness. So they created, so Hales in 2003 initiated a project to write down this massive proof in a completely formalized way so that a standard proof assistant could verify it. He estimated it would take 20 years to make this work. And so with he gathered 21 collaborators. It actually only took 11 years. Yeah, eventually what they did was that they first created a blueprint, you know, so a human-readable version of the proof, breaking things up into very, very small steps, and then they formalized each step bit by bit. And it was finally done. And then there was so they published a paper about the formalization, and that only appeared in 2017. So this was sort of the state of the art of formalization, you know, as of, say, 20 years ago. You know, like, it was possible to formalize big, complicated results, but it took enormous amounts of effort. You know, not something which you would do routinely. There was a more recent effort in a similar spirit by Peter Schulze. He called it the liquid tensor experiment. So Schulze introduced this theory of condensed mathematics, which is, all right, this is really far from my own area of expertise, but basically there are certain problems with, certain types of mathematics, you want to work in various categories. Like categories of topological abelian groups and topological vector spaces. And there's a problem that they're not abelian categories, that they don't have a good notion of kernel and co-kernel, and things don't work out properly. So he proposed replacing all of these standard categories with a more fancy version called a condensed category, which has better category theoretic properties. And so the hope then is that you can use a lot more high-powered algebra to attack, to handle things with topological structure or analytical structure, like function spaces, for example, Banach spaces. But in order for the theory to work, there's a certain vanishing theorem which I've written there, but I cannot explain to you. Okay, so there's a certain category, condensed abelian groups, and there's a certain X group involving P Banach spaces that has to vanish. This vanishing theorem is needed in order for all of the rest of the theory to actually be useful. If you want to apply it to functional analysis in particular. And so Schulze wrote a blog post about this. He said, you know, I spent much of 2019 obsessed with the proof of this theorem, almost getting crazy over it. In the end, we were able to get an argument pinned down on paper, but I think no one else has ever dared to look at the details of this, and I still have some lingering doubts. With this hope, with this theorem, the hope that the condensed formulas can be fruitfully applied to functional analysis stands or falls. Being 99% sure is not enough because this theorem is of the most utmost fundamental importance. He says, I think this may be my most important theorem to date, which is a really big claim, actually. Better be sure it's correct. So this was another case where there was a great desire to formalize the proof. So he asked publicly on the internet for help to formalize this in a modern proof-assistant language called Lean. And so, again, about 20 people, I think, joined this project to help out. And so Lean is based on, it has this philosophy where it has this single huge library of mathematical theorems, like the fundamental theorem of calculus or the classification of finite abelian groups. Like a lot of the basic theorems of mathematics are already formalized in this big library, and the idea is to just keep building on this library and adding to it with additional projects. But one of the problems that Schwarzer faced was that a lot of the basic tools that you needed, like homological algebra and sheaf theory and topos theory, weren't actually in the library yet. So actually part of what they had to do was actually set up the foundations of that theory and formalize it in the library first. But it basically was done in about 2 years. In 1 year, they formalized a key subtheorem, and then the whole thing was formalized about a year afterwards. It did have some, in addition to sort of making reassuring Peter that everything was correct, there was some other minor benefits. So first of all, there were actually a few minor errors in the proof that were discovered in the formalization progress, but they could all be fixed. Also, some small simplifications. There was one big simplification actually. So the original proof used something very complicated, which I also don't understand, called the Breen-Deligne resolution. But in the course of formalizing it, it was too hard to actually formalize this theory. But they found that there was a weaker version of this theory, which was good enough to formalize this application. But this was actually a major discovery, because this weaker theory could also potentially attack some other problems that the Breen-Deligne resolution is not well suited for. And now the math library is much better it has a lot of support for homological algebra and sheaf theory and lots of other things, which helped other formalization projects become easier. I got interested in this formalization a few months ago. Hang on. I should say, like with the Kepler experiment, so you don't just directly transfer a paper from the archive or something into Lean. What we found is that it really helps to create first an intermediate document, so halfway between a human readable proof and a formal proof, which we call a blueprint. So it looks like a human proof and is written in a version of LaTeX. But like each step in the proof is linked to a lemma in Lean. And so it's very tightly integrated. And it has a very nice, there's a very nice feature. It can create dependency graphs, which I'll show you an example later. You can see which parts of the proof have been formalized, which ones are not, and what depends on what. And it gives a lot of structure to the process of writing a paper, which right now we do by hand without sort of much assistance really. Yeah, Schwarzer said that the process of writing the blueprint really helped him understand the proof a lot better. And actually, people have been also going the other way. There's also software that takes formal proofs, which are written in something that looks like computer code, and turns them back into human readable proofs. Here is a prototype software. So there's this theorem in topology. Okay, I think it's if a function is continuous on a dense set and there's some extra properties, then it's continuous. It extends to a continuous function globally. And the proof was written first in Lean, but then it was automatically converted into a human proof, human readable proof. But again, where every step you can expand and contract. Like if there's a step you want to explain more, you can double click it and it will expand out, give all the justification. And you can click at any given point in the proof, and it will tell you what the hypotheses are currently, what you're trying to prove, and you can give a lot of structure. I think eventually textbooks. This is maybe a good format, say for undergraduate textbooks, to have proofs of, say, tricky theorems and analysis or something written in a way where, not in a static way, but where you can really, drill down all the way down to the basic axioms if you wanted to. Okay. One thing notable about these formalization projects is that they allow massive collaborations. In other sciences, people collaborate with 20 people, 500 people, 5,000 people. But in mathematics, still, we don't really collaborate in really large groups. 5 is kind of the maximum usually. And part of it is that, if you want to collaborate with 20 people, if you don't already know these 20 people and you don't completely trust that they're doing correct mathematics, it's very difficult because everyone has to check everyone else's contribution. But with a proof assistant, the proof assistant provides a formal guarantee. And so you can really collaborate with 20, hundreds of people that you've never met before. And you don't need to trust them because they upload code and the lean compiler verifies, yes, this actually solves the problem they claimed, and then you can accept it or it doesn't. So I experienced this myself because I got interested in formalization a few months ago. So I'd recently proven a combinatorial theorem with Tim Gowers, Ben Green, and Freddie Manners. It solved something called the polynomial Feynman-Ruzha conjecture. The precise conjecture is not important for this talk. It's a conjecture in combinatorics. You have a subset of a finite field vector space of small doubling, and you want to show that it is very close to actually being a coset of a subgroup. This was a statement that was in additive combinatorics that was highly sought after. So we had a 33-page paper recently proving this, mostly self-contained, fortunately. So I thought it was a good candidate for formalization. So I asked on an internet forum specializing in lean for help to formalize it, and then again, like 20, 30 people joined in, and it actually only took 3 weeks to formalize. So the time taken to formalize these projects is going down quite a bit. So in particular, the time taken to formalize this project was roughly about the same time it took for us to write the paper in the first place. And by the time we submitted the paper, we were actually able to put as a note that it was actually, the proof has actually been formalized. So as I said, it uses this thing called a blueprint, which splits up the proof into lots and lots of little pieces. And so it creates this nice little float, this little dependency graph. So this is a picture of the graph at an early stage of the project. So there's this node down the bottom called PFR. Maybe only the people in the front can see it. That's the final theorem that we're trying to prove. At the time of the screenshot, this was white, which means that it had not been proved, but not even been stated properly. So in fact, even before you prove the theorem, you have to first state it, and then you have to make definitions and so forth. Blue are things that have been defined but not yet proven, and green have been things that have been proven. And so at any state of at any point in time, some bubbles are white, some bubbles are blue, and some results depend on some others. And so the way the formalization proceeded was that different people just grabbed a node that was ready to be formalized because maybe all the previous results, all the results that it depended on were formalized, and they just formalized that one step independent of everybody else. And you didn't really need to coordinate too much. I mean, we did coordinate on an internet forum, but each little node is completely specified. There's a very precise definition and a very precise thing to prove, and we just need the proof. And we really don't care exactly what the proof is. I mean, it has to be not massively long. But so people just picked up individual claims. Like here's one very simple claim. There's a certain functional called Ruzha distance D, and there's a very simple claim that it was non-negative. And this turns out to have a 3-line proof, assuming some previous facts that were also on the blueprint. And so people just sort of picked up these things separately, and over time it just filled up. This is what a typical step in the proof looks like. This is the proof that this Ruzha distance is non-negative. This is the code in lean. It looks kind of a little bit like mathematics, but it is actually, if you've once you're familiar with the syntax, it actually reads, it's like reading LaTeX. The first time you read LaTeX, it looks like a whole bunch of a mess of symbols. But every line corresponds to a sentence in mathematical English. For example, the first line, if you want to prove that this distance is positive, it suffices to prove that twice the distance is positive. So you work with twice the distance because it turns out there's another lemma that bounds twice the distance. So yeah, every step actually, it corresponds reasonably well to the way we think about write mathematical proofs. Yeah, so fortunately the proof didn't reveal any major issues. There were some typos, but very, very minor picked up. And we also, there were some things we needed, again, we needed to add to the math library. There was the math library, we used Shannon entropy, and Shannon entropy was not in the math library, now it is. One thing about formalization is that it still takes longer to formalize proofs than to write them. And maybe about 10 times longer, I would say. Which is unfortunate. If it was faster to formalize, to write the proofs formally than to write them by hand, I think then that would be a tipping point. And then I think a lot of us would switch over, just because to get the guarantee of correctness. So we're not there yet. It is definitely getting a lot faster than it was before. But one thing we noticed is that actually, while it still takes a long time to write a proof, if you want to modify a proof to change some parameters and make it a little bit better, that can be done much quicker in the formal setting than with a paper proof, because with paper proof, if you change all your little parameters and so forth, you're likely to make also mistakes, and then you go back and it's a very annoying process. But it's actually much easier to modify an existing formal proof than to create one from scratch. For example, we were able, there's a constant 12, an exponent that appeared in our proof. A few days afterwards, someone posted an improvement in the argument that improved 12 to 11, and in a few days we were able to adapt the formal proof to do that as well. Yeah, and because you can collaborate, I think the process is scalable. There's just recently, Kevin Buzzard, for example, launched a 5-year project. The aim is to formalize Fermat's last theorem, the proof. And that is quite a big goal, because there are lots and lots of sub-portions that have had no formal proof at all. So that, I think, will be quite an ambitious project, but I think it's now doable. It wasn't doable 5 years ago, but now I think it is. Okay, so that's formal proofs. Okay, I might actually have to speed up a little. Okay, so, all right, so machine learning has, using neural networks has become also more and more commonplace in different areas of mathematics. I think I'll skip over this one. So one place where it is being used is in PDE to construct candidate approximate solutions for various problems. So so there's a famous problem in fluid equations, do the Navier-Stokes equations blow up in finite time, do the Euler equations blow up in finite time. Navier-Stokes is still challenging, but Euler, there's been a lot of progress recently that people have been starting to construct self-similar solutions to the Euler equations with some asterisks, but the asterisks are slowly being removed. And one of the strategies of proof is to first construct an approximate solution, approximately self-similar solution that looks like it's going to blow up, and then use some rigorous perturbation theory to perturb that to an actually blowing up solution. And machine learning has turned out to be useful to actually generate these approximate solutions. But I'm going to skip that for lack of time. I'll tell you, my favorite application of machine learning to mathematics is in knot theory. So this is a recent work. So knots are a very old subject in mathematics, and there's lots of, one of the fundamental things you study in knots is knot invariance. So there's various statistics you can study, you can assign to a knot, which depends on the topology of the knot or the geometry of the knot. So there's something called the signature, which is a combinatorial invariant. There are these famous polynomials, like the Jonas polynomial and Homfly polynomial. Then there are these things called hyperbolic invariants. The complement of a knot is often a hyperbolic space, and then you can talk about the volume of that space and some other geometric invariants. And so there are these massive databases of knots. You can generate millions of knots, and you can compute all these invariants. But they come from very different areas of mathematics. So some knot invariants come from combinatorics, some come from operator algebras, some come from hyperbolic geometry, and it's not obvious how they're related. But what these mathematicians did was that they trained a neural network on this big database of knots, and they studied the hyperbolic invariance and the signature, which is the combinatorial invariant. And they found that you could train the network to predict the signature from the hyperbolic invariant with like 99% accuracy. So they used like half the data to train the set and then half the data to test the set, to test the neural network. And so what this told them is that there must be some connection. The signature of a knot must somehow be a function, or at least very closely related to a function of a hyperbolic invariance. But the problem with neural nets is that they give you a functional relationship, or at least a conjectural functional relationship, but it's this massively complicated function. You compose hundreds and hundreds of nonlinear functions together, and it doesn't give you any insight as to what the relationship is. It just tells you that there is a connection. But it's possible to do some analysis. So they actually tried a very basic thing which happened to work. It's what's called a saliency analysis. So this neural network gave them this function. Basically, they fed in 20 hyperbolic invariants as input, and the signature as output. So it's basically a function from r to the 20 to the integers, I think. And what they started doing is that once they had this function, they just tested how sensitive the function was to each of its inputs. So they just varied one of the 20 variables, and they saw what happened to the output. And what they found was that only 3 of the 20 variables were actually important. That only 3 of them had a significant influence on the function. The other 17 were basically not relevant at all. And so they focused on those 3 variables, and they started plotting this function just restricted to those 3 variables. And that's just low enough dimension that you can eyeball the relationships. So they started plotting the signatures as a function of 2 or 3 of these variables and using color and so forth. And they started seeing patterns, and they could use these patterns to conjecture various inequalities and various relationships. It turns out that the first few inequalities they conjectured were false, and they could use the neural net and the data set to confirm this. But with a bit of back and forth, they were able to eventually settle upon a correct conjecture relating these invariants to the signature. And it wasn't the invariance that they expected. So yeah, it was these. They were expecting the hyperbolic volume, for example, to be really important. It turned out not to be relevant at all. But once they found the right variables and the right conjecture inequality, it suggested the proof. And then they were able to actually find a rigorous proof of the inequality that they conjectured. So it was a very nice back and forth between using the machine learning tool to suggest the way forward, but then going back to sort of traditional mathematics to prove things. Okay, so of course the most high-profile development these days has been large language models like GPT, and sometimes they work really, really well. So here is an example of GPT-4, which is OpenAI's most advanced large language model, actually solving a problem from the IMO, the International Mathematical Olympiad. And so it's a question. There's a function that obeys a certain functional equation. Can you prove? Can you solve for the function? And it actually happens to give a completely correct proof. Now this is an extremely cherry-picked example. I think they tried, from this paper, they tried all the recent IMO problems, and they could solve like 1% of the problems of this method. Famously, it's bad even at basic arithmetic. You ask it to solve 7 times 4 plus 8 times 8, and it'll give you the wrong answer. It gives you 120, and then it will keep going and say, and I'll explain why. And during the course of the explanation, it will actually make a mistake. And then you point out that they made a mistake and say, oh, I'm sorry, the previous answer was incorrect. I mean, these large language models, they remind me a lot of, if you have sort of a somewhat weak undergraduate student in office hours, and you ask them to solve a problem at the blackboard with no aids, he or she will try their best, and try to generate something that looks like a proof, but they don't really have a good way of correcting themselves. So sometimes they work really well, but often they're very, very unreliable. But there's lots of interesting recent experiments where you can couple these language models to other much more reliable tools to do mathematics. So for example, GPT now comes with plugins for Wolfram Alpha. So now if you ask Wolfram GPT to do an arithmetic calculation, it knows better than to try to do it itself. It will outsource it to Wolfram Alpha. Then there are more recent examples where people are coupling these large language models to a proof verifier like Lean. So you ask it to prove a statement, prove that the union of 2 open sets is open. If you ask a raw large language model, it will give you the statement a proof that looks like a proof, but there's lots of little logical errors in the proof. But you can force it to output in Lean, get Lean to compile, and if there's a compilation error, it will send back the error to the large language model and have to correct it and create a feedback loop. And it can actually be used to solve roughly sort of undergraduate math homework level problems by this technique with, but now with 100% guarantee of accuracy, if it works. I mean, of course, sometimes it will just get stuck and give up because it can never get the lean compiler to accept the argument. But it is beginning to make some headway. As I said before, I do find it can be useful as a muse, kind of like if you're just starting on a project. I recently was trying to prove some combinatorial identity, and I was thinking of using. I had some ideas in mind. I was going to use some asymptotics, work with some special cases, but nothing was working. And I asked GPT for some suggestions, and it gave me some suggestions I was already thinking of, plus some suggestions that were either completely vacuous or wrong. But it did tell me that you should probably use generating functions, which I should have known. But at the time, it escaped me. And just with with that hint, I was able to actually get the thing to work. So I mean, as just kind of someone to sort of double check your thought process, it is sort of useful. Still not great, but it has some potential use. There was another tool which I do like, and I use more and more now. It's integrated into something called VS Code, which is an editor to write code, but it can also be used for LaTeX. Something called GitHub Copilot. It's basically an AI-powered autocomplete. And you type in your code or your LaTeX or whatever, and based on all the text that you've already written, it will suggest a possible new sentence to generate. And so it can be very useful for code. You write down 3 lines of code and it suggests the 4th. And sometimes it'll get exactly right. Sometimes it's not exactly right. Sometimes it's complete rubbish. But then you can accept it, and it can save a lot of time, especially if you're doing some very menial code where you're repeating something over and over again. It works for LaTeX. I wrote a LaTeX blog post actually recently where I was trying to estimate an integral, and I broke up the integral into 3 pieces. I said, okay, the first piece I can estimate by this technique, and I wrote down how to estimate this technique. And then the Copilot has just suggested how to estimate the second term, and actually a completely correct argument. It was just a modification of what I had already written. So it's very good at just modifying text that you've already appeared. And it's slowly being integrated into proof systems like Lean. So it's to the point where sort of 1-line proofs, 2-line proofs, we can kind of get the AI to fill in for us. The kind of steps that correspond to like, this is obvious, or clearly this is true in a paper proof. I mean, not all of them, but we can get to the point where the AI can fill in a lot of them, and that will make proof formalization a lot faster. So there's a lot of potential. A lot of these technologies are very, very close to prime time, but not quite. It's still like it took me a month to learn Lean and so forth. They're still not completely usable out of the box, but they are beginning to be more and more useful, and in surprising areas. You wouldn't have expected, say, knot theory to benefit from these tools, but they do. They can't solve math problems on their own, except maybe undergraduate level homework questions, maybe is the current level. But as an assistant, I think they can be very, very useful. They can generate conjectures. They can uncover connections that you wouldn't normally guess. Once proof automation becomes easier and scales better, we may be able to do completely new types of mathematics that we don't do right now. Right now we prove things one at a time. I mean, we're still kind of craftsmen. We take one theorem and we prove it, and we take another theorem and we prove it. Eventually you could automate theorem proofs like exploring an entire theorem space. Of millions of different statements, and say, which ones are true, which ones are obviously false, and you could explore the geometry of theorems themselves. I think that we're going to see a lot of different ways to do mathematics, and we're going to see a lot of different ways to make connections in fields that we don't currently. And it'd be a lot easier to collaborate and work in different areas of mathematics. Especially because you can use these tools to sort of compartmentalize all these tasks, all these big complicated projects into small pieces. And plus also these large language models actually will become very good at getting humans up to speed on any number of advanced mathematical topics. Okay, oops. Yeah, again, it's still not quite there yet. I would say, if, for example, with proof formalization, it still takes about 10 to 20 times longer to formalize a proof than to do it by hand, but it's dropping. And I see no reason why this ratio cannot drop below 1. Eventually, it will become faster eventually we may just explain all our proofs to GPT, and GPT will generate, it will ask questions whenever we're unclear, but then it will just generate the LaTeX and the lean and stuff for us. And eventually, and check our work at the same time. So I think this is all in the future. All right. So thanks for listening. Yeah.
Thank you. That was lovely. I think we have a couple minutes for a few short questions. Is there a microphone?
Yeah.
There will also be a Q&A next door in 204 for a few minutes after when this is over.
Are we using these mics, or are we calling up people from the audience?
That's great. I can't see the mic from here. So the person I called on can ask the question.
Okay, sure. So one prediction that some people have bandied about advances with AI-assisted theorem provers is that we might enter a period where there's a proliferation of proofs that for new theorems that are formally verifiable, but which we don't yet have the technology to translate into forms that are easily comprehensible by humans. Do you see this being an issue?
Well, it already happens. For example, this Boolean Pythagorean triples theorem. No human will ever read that proof. I mean, I think it's actually not that scary. I mean, we rely on big numerical computations already in a lot of fields of mathematics. Of course, we would still want to have a human understandable proof, but as the not theory example shows, you can take an incomprehensible computer proof and still analyze it and extract out from it a human proof. So I think that will be one of the ways we do mathematics in the future is to clarify computer-assisted proofs and make them human understandable.
Thank you.
Can I ask you over there to ask your question?
My question is kind of speculative, but I wanted to ask your opinion on the role of human intuition going forward with this. Because a lot of what we talked about is formalization of human intuition into formal mathematics. Mm-hmm. I was wondering if you think that intuitive part of coming up with the idea for the proof itself could be automated in the near future.
Not in the near future. As I said, these large language models can generate things that resemble intuition, but it has a lot of garbage. At the very low level of proving like 1 or 2 steps in a proof, we can use these proof assistants to sort of only pick out the good intuition and discard the bad one. But what large language models are terrible at right now is is differentiating good ideas from bad ideas. They just generate ideas. So unless there's another breakthrough in AI, I don't think this is going to happen anytime soon.
Okay, we'll take one more question from this side.
So I was curious about the need for blueprints. Mm-hmm. Is it that the system doesn't know enough definitions yet, or is the proof space too big? Some combination thereof? No, it's more of an organizational tool for the humans. Okay, so if you want to coordinate 20 people to work on the same project, no one person, like many of the people who work on these projects, they don't understand the whole proof. So you need some structure to split it up into really small pieces, really atomic pieces that are self-contained for individual people to work on. So it's not for the computer. The computer can compile anything. It's for the humans to break up a complicated problem into lots of easy pieces.
Kind of like how division of labor works in like modern industries, like factories.
Okay, I'm going to invite all the other people waiting to ask questions to join us in room 204 briefly, and let's thank Terry for a lovely talk.